Okay, let's talk about bioseparation, meaning separation of biological molecules, including your proteins. So, the entire downstream processing, including clarification, would be considered a bioseparation, right? So, why do we do that? Of course, you are interested in capturing the target molecule, normally the API. Right? So where do you get that from? Of course, the cells, living cells, maybe plants and animals, or whatever the cell, genetically engineered cells you're using. So in the bio manufacturing industry, of course, upstream downstream processes are considered as the bioseparation process, right? So yeah, that's what we already talked about. And what kind of strategies do you have to keep in mind when you design your bioseparation method? Okay, so you have to have a very high purity, 99.99% purity of API, nothing else. Yeah, okay, you have to have a good yield. If you're starting out with a lot of API in big batch with a lot of contaminants, you don't want to lose your API. You can only effectively remove contaminants. That is a good yield, right? And cost, you don't want to spend too much money in your purification system. So these are the main factors you need to consider. Take a look at your textbook, tables and figures. There will be some additional explanation there. So the yield is defined as percent recovery, how much of the the entire mixture of molecule you're starting with, and how much of your API, the target molecule, you still recover at the end of your purification process. That matters, right? And then how do you analyze the purity and the yield of a product after each purification step? Of course, these are the ways. Maybe specific sensitivity, amount of the protein of interest divided by the total amount of protein in the sample. Okay, that was the activity, and at the end they should go up from one purification step to the next one. Okay, so as the purification proceeds, the specific activity of the protein of interest should increase efficiently. Okay, makes sense, right? And protein assay is routinely done. Okay, of course, you did the protein assay in the previous class, BIOT assay, to quantify the amount of protein you have. Okay, makes sense, right? And the enzymatic assay, if your target molecule happen to be the enzyme, you need to make sure that your target molecule is still in the right structure and still it is maintaining its activity, because without this activity your target molecule is become garbage, right? So make sure that activity is still there. So you have to observe its activity by maybe adding the substrate and by looking at the conversion of substrate into the product. Okay, and in describing enzymatic activity, there's an international enzymatic unit. Okay, so understand that, and system international unit. So if you're dealing with the enzyme, that may be an important factor. And requirements of biotech industry, of course, purification strategy for regulated commercial products such as like injectable drugs and things like the FDA is concerned in your purification method. So there are, federal and state regulations that oversees the process. So your purification method should be reviewed and approved by the FDA. That's what it means. And then once your purification method is approved, when you file your IND, okay, you have all these method, described. So FDA will have a look at it, and then they give you approval or not. Okay, but if the FDA approval is given, then it should be rigorously followed without any deviation and changes. Okay, if you want to change approved method, that's going to take a lot of time, so you better not change it. Okay, and then the products from recombinant DNA producing system should be produced after considering specific concern. Describe it, because so many people are concerned with the recombinant DNA, so there are guidelines about using those. Take a look at your textbook about that. And then here's the important part: parameters for separating method selection. When you try to select good separation method, what things do you need to look for? Okay, the properties of the molecule that you are dealing with is the most important part. Okay, so you can choose the size-based separation method. Okay, such as what filtration is a good example. So if your target molecule has certain size, maybe anything that's smaller, anything that's larger can be removed using a filtration, right? And the molecular charge may be a factor you can consider. Let's say your protein is positively charged, then maybe it may be captured by the negatively charged resin, column resin. The molecules will not be, negatively charged molecules will not be captured. So you can use that strategy. And the relative solubility to water or other solvent. Okay, if your protein is very soluble, it'll stay as solution, while other proteins and molecules will be precipitated out. So you can use that purification method. And relatively solubility in presence of salt, yes, depends on the salt concentration. Some proteins may be, aggregated, coming out as precipitants. So you can use that as a separation method. Sensitivity to pH, light, oxygen, and heat. Those are important during your purification process. You don't want to lose your protein, their integrity, structure, and activity. So make sure you preserve your protein very well against these treatments. And the affinity. Affinity is what? It's a structure-based interaction between your target protein and then maybe your antibody against it, or some kind of a receptor binding to it. So yeah, these will provide you with very specific purification strategy. Okay, very expensive method. So these are all important. Okay. And selectivity of the separation technique depends on its ability to separate a specific component from a mix based on molecular properties. Makes sense. Okay. If the highest product yield can be obtained with the fewest steps, it is ideal. What does that mean? Okay, you can only try 3 purification methods. You can capture your target molecule at 99.99 purity. Yeah, that's it. You don't need any more step because that'll be cheaper. You don't spend more money. You're gonna have a better return. That's what it means. Okay, so you can apply a low resolution method and then move up to the higher resolution to capture your target molecule. So take a look at that strategy in your textbook. And let's talk about various separation method. So number 1, fractionation and clarification. We already talked about clarification, right? Centrifugation or depth filtration. You can remove large chunky stuff. Okay, fractionation as well. You can separate out based on some differences. So think about your cell culture. Maybe you have a large amount of cells grouped together, clumped together. Sometimes you may have to break open the cells to capture your protein. Okay, then you may have to consider the lysis, cell lysis method of different kind. Okay, and then among the different kind, maybe French press method or sonication method, or maybe you can apply maybe some enzymes or treatment of different kinds, and you can choose the best method that's most effective for your protein. Okay, after lysis is done, solid matters, large chunky stuff should be removed from other things. That could be a clarification. If you don't have to break up your cells, that's even cleaner. It's better actually. If you can design your gene in your recombinant cell, that those cells will make the protein and then they will secrete out your protein, that will be a much more efficient method because you don't have to mess up with the cell breakage step. Okay, so that's a better designing. So once the clarification is done, you will try to capture your protein using different methods. So among those different methods, there are some low resolution method, meaning you cannot separate out molecules that are sharing the similar characteristics, but you can separate out molecules that are very different. Okay, so these are kind of low technology based method, or these are kind of cheap method, and these can remove many proteins without spending a lot of money. Okay, those are the low resolution method. But if your proteins are very similar in their sizes or their molecular weight, these methods do not work. Okay, number 1 method is called extraction. Okay, extraction means the solubility of a specific molecule to one medium is different from that of different molecules. So it's a solubility difference based method. Okay, so maybe your protein is hydrophobic
in certain solvent, but other contaminants are not hydrophobic, you can use that difference to remove your contaminants. Example is phenylchloroform extraction. A lot of proteins will be extracted using phenylchloroform, but your DNA, RNA can be staying as a solution. So it's an easy method, cheap method as well. Number 2 low resolution method is called precipitation. Okay, based on the difference between the molecules in their tendency to precipitate in certain solution, particularly liquid. Precipitate means what? They are not dissolved, they are coming down as a pellet. Okay, that's what precipitation means. Okay, so this desired product or impurities can be precipitated out from a solution. Okay, so you can maybe increase the salt in your solution, then maybe contaminants may come out as pellet or precipitates while your protein may be still in the solution, or it could be the other way around. Okay, you can increase salt, pH, temperature, alcohol, or some organic polymers, then you can change the precipitating conditions. By doing so, you can remove or you can capture your molecules. Ammonium sulfate precipitation or ethanol precipitation is well known. So those are 2 examples of low resolution separation method. What are those again? Extraction and precipitation. Okay. And then high resolution method, more expensive, but the method that will allow you to separate out molecules that have similar properties, characteristics. Those are high resolution method. Examples are like your gel electrophoresis. Okay, so DNA molecules that have similar sizes can be still sorted out, separated out. If you do electrophoresis, we already talked about them, right? Agar shell electrophoresis or PAGE, if you're dealing with a protein. Okay. So we already talked about those. So those are good examples. Okay, so that's it for the lecture 2. It's a very lengthy lecture, so I have about 5 segments. Okay, thanks.